So we will continue our investigation into the quantum mechanics of a single particle moving in a central potential. Right? The central potential again is something, a potential that depends only on the absolute distance of the particle from the origin and not on the angular coordinates. Okay, so let's briefly recap our strategy here. The strategy here was to look for simultaneous eigenfunctions of the Hamiltonian and L squared and L3. Okay, and the way we did this was to first look at the Schrodinger equation, the complete Schrodinger equation for psi. So investigate a Schrodinger equation for psi of r theta phi, and then we argued that for r very close to 0, psi of r theta phi should take the form RL times some function of theta phi alone. Okay, and then we demonstrated that for distances very close to the origin, this Schrodinger equation basically boils down to an eigenvalue equation for L squared equals, we actually got h bar square LL plus 1 psi of r theta phi, and specifically it is the y part, that is the angular part, that is an eigenfunction of L square operator. So we can actually write L square y of theta phi equals h bar square LL plus 1 y of theta phi. And then we argued that since we are looking for simultaneous eigenfunctions of h, L square and L3, so L3 acting on y theta phi, we argued should be equal to mh bar y theta phi. And we argued that since we are looking for simultaneous eigenfunctions of L square, L3 and h, the angular dependence should stay as y of theta phi because those are the eigenfunctions of the L square operator. So at most, as you move away from the origin, we then argued that for any r, the wave function in the central potential should take the form some function that depends on r alone and some function that depends on theta and phi alone. Is everyone able to hear me?
Yes, sir.
Yes, sir.
Okay, so somebody is saying that he's not able to hear me. So maybe you can check your speaker or something, or try reconnecting. Yeah, okay. All right. So this is what we argued. We argued that psi of r theta phi for any finite r, not just for small r, should have the general form, some function that depends on r alone, some function that depends on theta and phi alone. And with this form, we are guaranteed that these psi's are now simultaneous eigenfunctions of h, L square and L3. Furthermore, we argued by looking at the particular form of L3, which is minus IH bar dd phi, that the phi part of y should have the form e to the im phi times some function of theta. Okay. And we also know from single valuedness of the wave function, if you do a one complete rotation, remember that in this angular coordinates, in spherical polar coordinates, r ranges from 0 to infinity and theta ranges from 0 to pi and phi ranges from 0 to 2 pi. And after a one complete 2 pi rotation, we have to get back to the exact same point, which restricts single valuedness of the wave function, restricts m to belong to the set of integers. Okay. So this is all the information we extracted out of the y, the angular part, and then we plugged this form of the wave function back in the Schrodinger equation. And since we know exactly how L square acts on y theta phi, so let's go back to the Schrodinger equation. Maybe I wrote it in the beginning of last lecture. Yeah, this is the one. So if you plug in this general form of psi of r theta phi, you see that the first piece here acts only on the radial part, capital R, right? So the y part does not matter here. Similarly, you can factor out the y part from all of these guys. L square acting on y is just some number times y. So you can basically cancel out y from this equation and write an equation just for the radial part alone. And this equation we wrote towards the end of last lecture, which is called the radial equation. We redefined variables as little u equals r times capital R. And in this little u formalism, the radial equation looks exactly like a Schrodinger equation for a particle traveling in a one-dimensional potential, with the caveat that here r goes only from 0 to infinity, and the effective potential is the actual potential in which the particle is moving plus some 1 over r square potential, which is a remnant of the L square part of the Schrodinger equation. Okay. Now, to get the complete wave function, of course, we would need to solve both for the y theta phi and the radial part u of r. But of course, we cannot make progress with the radial equation unless we know what v of r is, right? So unless we know what v of r we are working with. So for today's lecture, we will hold the radial equation as such, and we will discuss a little bit more about the angular part. And once we take specific examples of v of r, like the Coulomb potential or the three-dimensional harmonic oscillator or something like that, then we can go ahead and for those particular potentials, we can simply plug them in the radial equation and solve this differential equation. So for now, we will keep the radial equation aside, and then we will push ahead with the angular part, y of theta comma phi. Okay. Now you might argue that we have done as much as possible with respect to y of theta comma phi. We have even figured out what the phi dependence is, and that is certainly true. But it turns out that by simple logic and deduction, we can actually claim quite a bit about these y of theta comma phi's and about these m's and things like. So that is what we will do in today's lecture. Okay, that is the stage for today's lecture. Are there any questions about any of this? Okay. So today's lecture will deal with this y of theta gamma phi, and these are special classes of functions, and these are called spherical harmonics. Again, my goal is not to solve the differential equation completely, but simply to motivate you how to think about these spherical harmonics. And then we will do the formal differential equation approach later. Okay, so what are these spherical harmonics? So remember that these are simultaneous eigenfunctions of L square and L3. So L square acting on y theta comma phi equals h bar square L plus 1 y theta comma phi. And since these y's carry information about both the theta part and the phi part, they are usually labeled by two indices, the L and the M. The M is the, remember, M is the angular quantum number of the L3 operator, and L basically is related to the eigenvalue of the L square operator. So since it carries information about the eigenvalues of L square and L3, it is labeled by two indices, L and M. M is the eigenvalue of L3, but L is not the eigenvalue of L square. It is related to the eigenvalue of L square. Similarly, L3 acting on y Lm of theta comma phi equals mh bar y Lm of theta comma phi. Okay, this is where we are. Okay, now let us actually recap one equation that we wrote down, and we'll just keep it aside for now. We will not use it, but we will use it toward the end of this lecture. We wrote down, if you remember right, a while ago, an equation for the del square operator in terms of just the r and the angular parts L square as 1 over r square ddr r square ddr minus L square over h bar square r square. I think this is an equation we wrote down maybe 2 classes ago. Okay. Oh, there is 2 questions. Can you please explain once again why the effective potential occurs? I mean, due to which quantity? So the effective potential basically occurs because there is an L square in the equation. So effective potential simply means it's just a name. It is the actual potential in which the particle is moving plus this 1 over r square times h bar square LL plus 1 piece. So remember that when you write down the Schrodinger equation, you can write it down like this, right? Now, what is the Schrodinger equation in 3 dimensions? The Schrodinger equation in 3 dimensions is basically del square psi equals h psi. The time independent Schrodinger equation is this, right? But it turns out that in 3 dimensions, del square, of course, is dependent on both r, theta, and phi, and I can write del square in this particular way, or where all the theta and phi differentiations can be clubbed in this very compact looking piece called L square over h bar square r square. Okay. So now simply plug this over here. You will get 1 over r square ddr, r square ddr acting on psi minus L square over h bar square r square acting on psi equals E psi. Okay, sorry, this is not just del square, this is just kinetic energy. The Schrodinger equation is minus h bar square over 2m del square psi plus v psi equals h psi, right? So I should multiply the whole thing here by minus h bar square over 2m. This is the kinetic energy piece, plus v psi equals E psi. This is the Schrodinger equation. Okay, and given our form of the wave function psi, which is r of r, y of theta comma phi, notice that the L square is only an operator that depends on theta and phi, and L square is y is an eigenfunction of L square. So L square acting on psi is basically r of r, with L square acting on y theta phi, which gives us h bar square LL plus 1 y. So this is basically h bar square LL plus 1 psi, because y times r is just psi. Okay, so it is this piece. So if you simply look at this piece and the potential piece, I can write these two together. There is a minus h bar square over 2 outside. So the whole thing becomes h bar square over 2m times 1 over h bar square r square. So I've been calling this mu, so I'll stick with this because there is another m here. H bar square r square times h bar square LL plus 1 psi. That is this guy, this whole piece. Okay, plus v of v times psi. So if we add these two guys, you get v of r, the h bar square cancels, and there is an overall h bar square outside, plus h bar square LL plus 1 divided by 2 mu r square times psi. Okay, so remember that this piece actually comes not from the potential energy part, but actually from the kinetic energy part. Okay, the kinetic energy part, the angular part of the kinetic energy operator. The angular part of the kinetic energy operator simply acts on the y's to give you h bar square LL plus 1 times the y, and that is why you get this very simple form, which is just 1 over r square times psi. And since this part has no mention about angles and has no differentials, I can as well club it along with the potential piece, because it is just a function of distance alone. So that's why we club this piece and the potential piece together to write down what is called an effective potential. That is where it comes from. This 1 over r square piece actually comes from the angular part of the kinetic energy operator. Another question, can you explain about the L and M and Y? Okay. So remember that y is a simultaneous eigenfunction of L square operator and L3 operator. The eigenvalue of L3 operator is m. So the y here should know something about m. The eigenvalue of the L square operator is L times L plus 1. So given L, I know the eigenvalue of L square. So the y should also know about the eigenvalue of the L square operator, which is related to L. So that is why we label the states by L and M. Which means, suppose if, now I've not told you, you know that L has to be an integer. We have not said anything about M yet, we will, but L has to be an integer, M has to be an integer. We have not said anything about the range of M, which we'll come to in just a second. But all we know at this stage is that these are eigenfunctions that label the state using two indices. Each state has these two indices, L and M, which are just integers. Okay, and the Y carries these labels. Any other questions? Is this clear?
Hello, sir.
Yes.
Sir, when you consider the effective potential, you took the angular momentum part, but that is come from kinetic energy. So why don't we say that this is the rotational kinetic energy instead of we add them in the effective potential?
The reason is, so you may call it whatever you want. The reason is because when all is said and done, all the information about the angles disappears from the equation because we are looking for eigenfunctions of L square. You see, if this psi were not an eigenfunction of L square, right? Think about that. If this psi were not an eigenfunction of L square, so let us look at the same Schrodinger equation: 2 mu times some d square dr square piece plus this L square piece. Yeah, roughly speaking, this was the structure, L square over R square piece. This acts on psi. If this psi is not an eigenfunction of L square, then this L square times psi would be some complicated function of theta, phi, and R. You see?
Yes, sir.
So there is no way I can club this along with the potential and call this an effective potential, because since we are dealing with central potentials that depend on distance alone, this doesn't fall in that class of central potentials because it has an explicit dependence on theta and phi. But since we are looking for simultaneous eigenfunctions of L square and H, the angular part very easily decouples because L square acting on psi is just some number times psi. Okay, so which is
Yes.
why the structure of this equation enables us to club this term with the V of R. But yes, absolutely, the 1 over R square piece actually comes from the rotational part. But after all, when you do the mathematics, it turns out that this rotational part is proportional to just 1 over R square with all the angular information gone. So that is why I'm clubbing with V of R. That is all. Also, another advantage of clubbing it with V of R is that this equation looks very much like a one-dimensional Schrodinger equation. So that's for which you are already familiar with. So from 3 dimensions, we have boiled down the equation to just 1 dimension. So that is another power of this assumption of central potential. See, once you assume that the potential doesn't depend on angles, you see that even without knowing the form of the potential, you can say a lot about the angular dependence of the wave function. In fact, you can nail down the angular dependence completely. And all you have to do is just solve for the radial part. Make sense?
Yes, sir.
Okay. All right. Okay. So let us actually remember our initial onslaughts, that psi very close to the origin, psi has the form r to the L y of theta comma phi. Okay. And this has again stopped working, so I'll have to reshare. Okay. Okay, so very close to the origin, my psi has this form, right? All right. Now, here's a fun exercise that you should do. Add del square on this r to the L times y, YLN. Okay, and use this equation. So this is your del square. Okay. So in fact, let me actually do this. This is equal to 0. I'll show you just the first step. Remember that del square psi would now be equal to 1 over r square ddr r square ddr of r to the L y minus L square over h bar square r to the L y. Okay. Now in the first piece, y is a function of angles alone, so you might as well pull out the y, and ddr acting on r to the L is something that you can easily figure out. In the second piece, L square is a function of theta and phi alone, and it doesn't depend on r at all, so you can pull out the r to the L, and L square y is just h bar square LL plus 1y. If you use these two facts, you'll be able to prove that this is equal to 0. Okay, this is a fact that you should keep at the back of your mind for now. Okay. So anyway, so if I want to investigate these y's, I don't have to use a general psi. I might as well look at the form of psi very close to the origin, because my angular dependence is y of theta comma phi, regardless of whether I'm close to the origin or far away from the origin. Okay. All right. So r to the l y lm of theta comma phi. Remember that y lm theta comma phi again is a function of angles alone. So r to the l y lm theta comma phi is a homogeneous polynomial in the r to the l y lm theta phi is a homogeneous polynomial of order L in the coordinates x1, x2, x3. You might be wondering why I go back to x1, x2, x3 now. The answer to this will become clear in about 5 minutes. Okay. It is some polynomial of order L in x1, x2, x3. Okay. Now, instead of using x1, x2, x3, I'm going to do a slight change of coordinates, so we can simply guess the form of these y's. So let us actually indulge me for 1 second. So x1 is r sine theta cosine phi, r sine theta sine phi, and x3 is r cosine theta, right? Now, this YLM should be a function of, so remember that YLM should be a function of just the unit vector sine theta cosine phi, sine theta sine phi, and cosine theta. Okay? All right. So now among these three guys, it is only x1 and x2 that has a dependence on phi. x3 doesn't have any dependence on phi. Okay? All right. Why is this important? Well, it is important because L3 is dd phi. Okay. So if YLM is a polynomial of x1, x2, and x3 in some sense, then we need to figure out how the eigenvalue equation for L3 looks like in this polynomial. So it is important to understand where the phi dependence comes from. So it comes from x1 and x2. Now, since we have to work out the eigenvalue equation, instead of having cosine phi's and sine phi's floating around, it's much simpler to work with a slightly different coordinate system for this problem. So I will define x plus as x1 plus ix2, and x minus as x1 minus ix2, and x3 I will leave alone. Okay. So from x1, x2, x3 coordinate system, I'm moving to x plus, x minus, x3 coordinate system. So what is x plus? X plus would be r sine theta cosine phi plus ir sine theta sine phi, which you can easily figure out looks like r sine theta e to the I. X minus looks like r sine theta e to the minus sine phi. And this is just r cosine theta. This is the first manipulation that I will do. Instead of working with x1, x2, x3, for now I will simply look at x plus, x minus, and x3. Now we will not stick with these three, with this coordinate system for long. Once we find out what we are seeking, then we will simply revert back to the x1, x2, x3 stuff. Okay. All right. So let us look at the eigenvalue equation for L3. L3 acting on YLM of theta comma phi is mh bar YLM theta comma phi. Okay. Now L3 is minus IH bar d phi YLM of theta comma phi is mh bar YLM of theta comma phi. Okay. So the h bar part can go away, and m, as we know, is an integer. Now our claim is that these YLMs are polynomials of order L in x1, x2, x3, or equivalently x plus, x minus, and x3. So in other words, let us say if y, so let us say that we are looking for L equal to 2. So y 2m, right? Then this is a polynomial. So this is a polynomial of order 2 in the coordinates, which means this y2m can contain terms like x plus square, x minus square, x plus x minus, x plus x3, x minus x3 and x3 square. Right? So this is a polynomial of order 2 in the coordinates. Similarly, y3m would have x plus cubed, x minus cubed, x plus square, x minus, and so on and so forth. Okay. Now, out of all these possible terms in YLM, it is only x plus and x minus that have an explicit phi dependence. Right? So let us say that you have a general polynomial of order L. Let us say that it has n plus factors of x plus and n minus factors of x minus. Okay. In general. So n plus can be 0, 1, 2, whatever it is. For example, in the y2m example above, in the first term, n plus is 2, n minus is 0. In the second term, n plus is 0, n minus is 2. In the third term, n plus is 1, n minus is also 1. In the fourth term, n plus is 1 and n minus is 0, and so on and so forth. So each term has some specific power of x plus and specific power of x minus, because x plus has e to the I phi and x minus has e to the I phi, and minus I phi and x3 has no phi's. We are simply counting the number of x pluses and x minuses in a specific term in this polynomial. Okay. Then this eigenvalue equation for YLM, it gives you m times YLM, and this m has to be equal to the difference in the number of factors of x plus and the number of factors of x minus. Is this obvious to you, or should I show this? Okay, so I will take silence as disagreement and I will show it. So let us take a specific term, right? So let us take a term that looks like x plus to the L minus 3 and x minus 3. Okay, this is a polynomial of order L, and I'm looking at some specific term which has L minus 3 factors of x plus and 3 factors of x minus. So if I act the minus I dd phi on this term, what do I get? So remember that this is L minus 3 factors of e to the I phi, and this is 3 factors of e to the minus I phi, right? So this is going to pull down I times L minus 3, and this is going to pull down minus 3i times x plus L minus 3, x minus cubed. Okay, why? Because x plus is e to the plus I phi. So dd phi of e to the I phi to the L minus 3 is simply I times L minus 3. And dd phi of x minus cubed is dd phi of e to the minus 3i phi, which is just minus 3i. Okay, so this I can rewrite as, if I take the I outside, this is simply L minus 3 minus 3. And L minus 3 is simply the number of factors of Lx plus in this equation. And this 3 is the number of factors of x minus in this equation. So the eigenvalue equation for L3, which is equal to m, is actually equal to the number of factors of x plus in any term in this polynomial minus the number of factors of x minus in that term in that polynomial. Is this clear or no? I'll erase this part and wait for you, or wait for a couple of people to either ask me any questions or tell me if it is clear. Is this okay? No, sir, I'm not able to get what we are doing. All right. So the first thing is that so let us look at this particular example, y2m. Okay, so we argued that a distance is very close to the origin. YLM is a polynomial of order L. Whatever the L is, it is a polynomial of order L in the coordinates x1, x2, x3, or equivalently x plus, x minus, and x3. Okay, so for example, y2m, you have terms like x plus square, x minus square, x plus x minus, x plus x3, x minus x3, x3 square, and so on, and no more. There is no other terms possible, at least close to the order. Okay. So then these YLMs are simultaneous eigenfunctions of both L square and L3. So let us look at the action of L3 on, let us say, Y2M. Okay. Now it should be clear to you that Y2M in general cannot be a linear sum of all possible terms of order 2. Okay, so I told you that Y2M can contain terms like x plus square, x minus square, x plus x minus, x plus x3, x minus x3, x3 square. But Y2M cannot be in general a linear combination of all these guys. Why? So let us actually investigate Y2M, and then I hope that the general discussion would be clear. So first of all, is it clear that Y2M can contain all these factors because it is a polynomial of order 2 in the x1, x2, x3 coordinates? Okay. So if there is any questions about this, please stop me. If not, I will go on. Now, let us look at the action of L3 on Y2M. Okay. No, sir, I'm not able to get what we are doing. I have. So what is it that you're not able to get? Okay, this was previously asked. All right. So let us look at the action of L3 on Y2M. Okay. Now, if Y2M contains all the terms that I've written above, then it will become inconsistent with the eigenvalue equation for L3, because L3 acting on Y2M should give you some number times Y2M. That is the eigenvalue equation, right? But x plus goes like e to the I5, x minus goes like e to the I5, and x3 has no phi dependence. So x plus square goes like e to the 2I5, x minus square goes like e to the minus 2I5, x plus x minus has no phi dependence, it goes to e to the 0 times phi, and x plus x3 goes like e to the I5, and so on and so forth, right? Now, if I add d phi on all these guys, it's the first term, it's going to pull out. So d phi of a x plus square plus b x minus square plus c x plus x minus plus d x plus x3 plus e x minus x3 plus f x3 square is going to look like a times 2I x plus square plus b times minus 2I x minus square plus c times x plus x minus has no phi dependence, so it will be 0, plus d times I times x plus x3 plus e times minus I times x plus x, sorry, x minus x3 plus f times again 0, because x3 has no phi dependence. Okay, so obviously you conclude that this general linear combination of all the possible terms of order 2 cannot be an eigenfunction of d phi operator, because eigenfunction means d phi acting on a function should give me something times the same function back. Okay, so we conclude that even for this very simple case, the form of these YLMs should be quite simple, because they can, even though we claim that the general case was a sum of all possible terms of order some L, we see that it cannot have all possible terms, because such a general polynomial will not be an eigenfunction of L3. So if it were to be an eigenfunction of L3, then I can have x plus square alone, because d phi acting on x plus square would be some 2 times x plus square, 2I times x plus square, okay, and so on and so forth. And d phi acting on, let us say, some factor that some other polynomial has x plus square and x minus, this would have, see, x plus square will bring in a factor of 2 and x minus will bring in a factor of minus 1. So this will be 2 minus 1 times x plus square x minus, and so on and so forth. Okay, so each one of these terms can be an eigenfunction of the DD5 operator, but a general sum of them cannot be an eigenfunction of the DD5 operator. And if you take a single term in this polynomial, the eigenvalue of that term is the number of factors of x plus minus the number of factors of x minus, because each x plus is going to pull out a factor of plus 1 and each x minus is going to pull out a factor of minus 1. So in general, this m, which is the eigenvalue of the DD5 operator, is going to be so let us erase all these things. So this m is going to be the number of factors of x plus in a specific term minus the number of factors of x minus in that term. Okay, because each factor of x plus DD5 is going to be I times e to the I5, and the I cancels, right? And each factor of minus I5 is going to pull out a factor of minus 1. Okay, so that is why this negative sign is there, because each n minus comes with a minus sign. Okay.
Hello, sir.
Yes.
Sir, can I say that x cubed square is the eigenfunction of del phi?
Yes. X cubed square. What?
No, sir. X not cube. X super subscript square.
Yes, you can. Yes, it is an eigenfunction of L3 with eigenvalue 0.
But sir, it has no phi dependence.
It has no phi dependence, but since we argued that, see, again, anything that has no phi dependence is a trivial eigenfunction with eigenvalue 0. I cannot exclude that, because in the space of polynomials, I cannot simply throw away terms. So I have to construct YLM such that it is the most general polynomial of order L. Okay. Now, among these XL, suppose if I'm looking at a particular value of M, it is possible that only some of these guys satisfy that particular thing. So let us actually take an example of Y to M, and then I will answer this question in more detail. Okay. So please hold on to this question for 5 minutes.
Okay, sir.
So let us look at this value of M. M is the number of factors of X plus and the number of factors of X minus. Now, what is the maximum and minimum value this M can take? So previously we argued that M was an integer based on single valuedness of the wave function. Now we are arguing that M is a difference between two integers. Now the maximum value of N plus is L. Okay, because for a polynomial of order L, there can be L factors of X plus. So the N plus you can have a term like this. Okay, with no X minus. So the maximum value of the number of X plus terms given in L is just L. The minimum value of N minus is 0, because you can pick a term that has no X minus. So the maximum value of M is L minus 0, which is L. And the minimum value of M is N plus could have 0 and N minus could have L values. So a term like this. So the minimum value is 0 minus L equals minus L. So M, for a given value of L, M cannot take more than L, or the minimum value cannot become more negative than minus L. So the value of M, which was previously an integer, is now found to be bounded given the value of L. So for a given L, M can take all values minus L plus 1, 0, L, L minus 1, L. Okay. So the total number of values, if you also count 0, is 2L plus 1. And 0 is also a perfectly valid number, because you can have a case where there is equal factors of n plus and n minus. For example, in this guy, this has a factor of 0 because there is one factor of x plus, one factor of x minus, it is 0. In fact, this term, to answer the question that was asked, also has m equal to 0 because here n plus is equal to 0 and n minus is equal to 0. So both these possibilities exist. Okay. So which means that for a given value of L, I can have 2L plus 1 values of n. So for example, for L equal to 2, there is 3 of these spherical harmonics, y2 minus 2. Sorry, there is 5 of these spherical harmonics. I cannot count apparently. y2, 2, y2, 1, y2, 0, y2, 1, y2, 2. Okay. And L equal to 1, there will be 3, y1, 1, y1, 0, and y1 minus 1. No more. Okay. So let us now start guessing, because that is the fun part. And we can always solve the differential equation and find out what these y's are, but it's easier to guess. Now, let us look at L equal to 0. L equal to 0 means m can only be 0. So there is only one spherical harmonic, y0, 0. Now, since y is a linear combination of polynomials of order 0, and polynomial of order 0 is just a constant, so y0, 0 should be just a constant. Okay, so this is trivial. L equal to 1. Okay, L equal to 1 can have 3 terms, x plus, x minus, and x3. There is 3 terms that are possible. Okay, so let us look at the 3 cases separately. So let us look at y, L equal to 1, and m equal to 1. So I have 3 terms to pick from, and I have to ask which one of these guys has m value equal to 1. Well, for m value equal to 1, I need only one factor of e to the I5. So only one of these guys fits the bill, x plus, because x minus has value, eigenvalue of L3 is minus 1. So here I'm looking at m value equal to plus 1. So y11 can only contain one factor of x plus, which means y11 up to a constant, some constant times x plus, which is sine theta e to the I5. Similarly, y10 should have an m value of minus 1, x plus has an m value of 1, x3 has an m value of 0, and x minus has an m value of minus 1. So only one of these terms is possible. So y10 should be just x minus. Sorry, not y10, y1 minus 1. And this should be some other constant, sine theta e to the minus I5. Okay, y10, again only 3 terms are possible for a polynomial of order 1, x plus, x minus, and x3. X plus has one factor of e to the I5, which means m value of 1. X minus has m value of minus 1. So only x3 is a possibility. So up to a constant, y10 should be some constant times x3, which is cosine theta. Okay, so without doing any mathematics, you can simply guess looking at the m values. You can do these guessing games only for very low values of L, as we will demonstrate. For very large values of L, it is not. L more than 2 is not possible. But anyway, if you actually solve the differential equation, this is what you would get. y11 should be e to the sine theta e to the I5, y1 minus 1 is sine theta e to the minus I5, and so on. So let us look at the L equal to 2 cases. L equal to 2 can contain terms like x plus square, x minus square, x3 square, x plus x minus, x plus x3, and x minus x3. That is all, nothing more. So let us look at y22. This is L equal to 2 with m value 2, which if I want m value 2, I need 2 factors of e to the I5, right? Because dd5 of e to the 2I5 is 2 times e to the 2I5. So I need x plus square, nothing else fits the bill. So y22 should go like x plus square, which means this is equal to something times x plus is sine theta e to the I phi. So x plus square should be sine square theta e to the 2 I phi. Nothing else is possible. Similarly, y2 minus 2 should go like x minus square, because I need a factor of minus 2, which is only possible with two factors of e to the minus I phi. So this will be some normalization times e to the minus 2 I phi. What is y21? Can anyone guess? It should be a polynomial of order 2, but m value of 1. Which one of
X
these?
plus x3
Very
or x minus x3.
x plus
नहीं, सिर्फ x plus ही.
x plus x3. So this should be some constant times x plus is sine theta e to the I phi, x3 is cosine theta. So this should be sine theta cosine theta e to the I phi. Similarly, y2 minus 1 should be x minus x3. So this should be sine theta cosine, e to the minus I phi. Now, here comes the tricky part. What is y20? It's a polynomial of order 2 in the x's, but with has an x with m value of 0. So this was pointed out earlier. An m value of 0 can be obtained in two different ways. It can be obtained by looking at a function that has no phi dependence, or it can be obtained by looking at a term that has equal numbers of x plus and x minus, right? Because m goes like n plus minus n minus. So if I look at a term that has equal number of x plus and x minus, that will have m equal to 0. Or if I look at a term in this set of polynomials that has no phi dependence, that will also have an m value of 0. So y20 you will find is actually a function of two of these guys. Either x plus x minus, which has an m value of 0, or x3 squared, which also has an m value of 0. So this can be a x3 squared times b x plus x minus. And now you're stuck because I don't know how to make progress, right? So I should just simply write this as this. But in this case, we're actually lucky. So this is the last thing I will do today, and I will stop. You can actually get the exact form of y20 also up to a normalization. And I will leave this as a homework for you, because I'll also put this in the tutorial problem. Because you have a constraint. What is the constraint? The constraint is del square acting on r to the L y Lm is equal to 0. Okay. And if you use this constraint, you would actually be able to get a relation between A and B. So let us apply this to y20. For y20, this constraint is L equal to 2, y20 equal to 0. Because this is true for any L, it has to be true for L equal to 2 also. So substitute this, substitute this over here, and you will be able to find that A should be equal to minus 2B. Okay, this is your homework. So what is A and what is 2B? So y20 in that sense is simply equal to A, so this is, I can write this as minus 2B x3 squared plus B x plus x minus. So this is equal to, I can take the overall B outside, that is just a normalization. So the sum constant times x plus x minus minus 2x3 squared. Okay. So this is some normalization times x plus x minus is sine theta e to the I phi times sine theta e to the minus I phi. So this will be sine square theta. And this is minus 2 cosine square theta. So you can prove that y20 goes like something times 3 cosine square theta minus 1. This will be the functional form of y20. Again, gotten by just guessing without solving any differential equations. But this is as far as you can go. When you try to guess the form of y31 and y32 and things like that, you will need more constraints. You will need to fix more relative normalizations, and you only have one constraint, so it won't be possible in general, I think. So these are the spherical harmonics, and spherical harmonics, when all is said and done, spherical harmonics are eigenfunctions of a Hermitian operator L square and L3, which means spherical harmonics have to be orthogonal in both the M index and the L index. So these overall normalizations are fixed by demanding that d omega YLM theta phi mod square equals 1. So you fix the overall normalization by demanding that the integral over all the angular part is just 1. So what d omega, if you don't know, is equal to theta equal to 0 to pi d theta sine theta, and phi equal to 0 to 2 pi d phi. Okay. And the YLMs are also orthogonal in L and phi, which means if I integrate YLM L prime M prime star YLM theta phi, I will get a delta function in LL prime and a delta function in MM prime. Okay, so the YLM theta phi are orthonormal functions of the angles theta phi, since they are the eigenfunctions of the Hermitian operators L square and L3. Okay. So that is as much as we can go about in this problem without solving the differential equation. So in the next week, I will write down the differential equation that these YLMs satisfy, and then we will sketch the solution of this in a tutorial problem. And then we will move on to the radial equation, and we will study the Coulomb potential 1 over R for the hydrogen atom, and then understand the spectrum of hydrogen atom. So that will be the homework for all of us for next week, or classwork for all of us next week. Okay. So I'll stop at this point, and you can ask me if you have any questions.